Well, good afternoon. Welcome to NASA headquarters in Washington. My name is Dwayne Brown with the Office of Communications. NASA's New Horizons research team is back to reveal even more unprecedented images and science that continue to be returned from the New Horizons spacecraft following its historic July 14th flyby of Pluto. But to set the stage for today's briefing, please welcome to the podium astronaut and head of the NASA Science Mission Directorate, where New Horizons is one of almost 100 science missions in the Directorate's portfolio. Ladies and gentlemen, Dr. John Grunsfeld.
Thank you very much, Dwayne. And this week has been just a phenomenal week. On Monday, we released the first image from the EPIC Earth Polychromatic Imaging Camera on the Discover mission, the Deep Space Climate Observatory, the Blue Marble. This is our first, true blue marble of the Earth since 1972, when the Apollo 17 astronauts took the famous blue marble image of the Earth. And it really paints, I think, just an incredible picture of our home planet and how, lucky and precious planet Earth is. Especially when you compare it to the amazing views we've recently gotten from the Dawn spacecraft, which is a somewhat Ceres hostile world, dwarf planet Ceres. We've just announced yesterday a Kepler discovery of a sort of a parallel, a cousin solar system to that of our own solar system, with a G-type star much like our sun, a little bit older, and an exoplanet that's about 60% bigger diameter than the Earth, right in the middle of the habitable zone. It's truly amazing, the things that we're doing. But the images that we've been getting and the science we've been getting from Pluto is really just been more than amazing, and proves definitively a scientific theory that science never sleeps. And if you look at our panel here, they actually look pretty cheery for a group of scientists that have not been sleeping for the last few weeks. But they are here to tell us about the most recent amazing results from the Pluto New Horizons mission. And I'm just thrilled to be here to hear those results.
Okay, So, we have, before I introduce our panelists for this afternoon, obviously the NASA accounts, social media buzz with this mission and the results and the images. Follow the NASA accounts on Twitter, YouTube, Facebook, and other NASA accounts. And send in your questions at hashtag #AskNASA. And a lot of questions are coming in. We'll try to answer those as quickly as possible, but keep them coming in. And you can follow the conversation, and there's still a lot of conversation all over the world on this historic mission at #PlutoFlyby. And again, online, all of the information today and in the future can be obtained by going to www.nasa.gov/New Horizons. First up, you will hear from Jim Green, Director of Planetary Science at NASA headquarters. Alan Stern, New Horizons Principal Investigator at Southwest Research Institute in Boulder, Colorado. Michael Summers, New Horizons Co-Investigator at George Mason University, Fairfax, Virginia. Kathy Olkin, New Horizons Deputy Project Scientist, also at the Southwest Research Institute. And William McKinnon, New Horizons Co-Investigator at Washington University in St. Louis. And with that, I'll turn it over to Jim.
Thank you very much, Dwayne. July 14th was very historic for NASA with our very successful flyby of the New Horizons spacecraft through the Pluto system. And we're just 10 days from that. And yet we've only had about an opportunity to see about 5% of the data. As many know, we stored that data on board as we flew through the system, and it's just now starting to come back. Each and every day, the science team has been huddled, looking at the data as it comes back, and is always surprised. And it's just quite a pleasure to be part of that team, to look at the data when it comes in and see the new discoveries that are coming out. Now, today we're going to talk about some of that latest data that came in within the last few days. This is a spectacular set of data, but it's also data that happened and was taken on board, stored prior to the encounter, and it's post-encounter, after the spacecraft had an opportunity to fly through the Pluto system and look back to Pluto as it's hurtling away at more than 16 kilometers per second. These are just amazing discoveries. And so without further ado, let me turn it over to the principal investigator, Alan Stern, to start it off. Alan?
Thank you, Jim. Well, as Jim said, last week, the United States, through our project and NASA, explored the farthest frontier ever explored by humankind, the Pluto system. And we can't tell you how happy we are just to be back as a team and to tell you what we've been discovering. We came back last Friday and gave a first report about just the first couple days of data download and the first reactions that we had to it. Now we're 10 days out, 7.5 million miles from Pluto. We've had more time to think about the data sets that are on the ground, and equally importantly, we have about 3 times as much data on the ground. Now, that, as Jim said, it's not very much of the total data load. We have about 4 to 5% of the data back. 95 or 96% of it is still on the spacecraft, so we're only scratching the surface, and we've got some great discoveries to tell you about. We also want to tell you that besides the data sets, there's one other way on this project to know that we've really done the exploration. We're on the other side of Pluto, and that's this bumper sticker that's inspired by Val Malder, our deputy systems engineer, that says, "My other vehicle explored Pluto." It's got a nice picture of Pluto made by New Horizons in the rearview mirror. That's how you know. Well, I want to say a few things, and I'd like to call up my first graphic, which is just a hauntingly beautiful image of the double planet system, Pluto-Charon, with Pluto on the left and Charon on the right. This was made a few days out on approach with true color added from our Ralph instrument on top of a LORRI image. And as I tell you a little bit about where we are in the mission, just feast your eyes on this. We've never been to a double planet system before, and it's turning out to just really be a scientific wonderland. We've now finished the first phase of downlink. That was an intensive 10-day period in which we sent down images and spectra and other data sets just to whet our appetites and tell us the basics about the Pluto system and the discoveries that you'll be hearing about by myself and Mike, Kathy, and Bill report on some of the most important findings that we've already made in these few days. We're now moving into a second phase of downlink that's a little bit different, and I think it's important that everyone understand that difference. We'll be transmitting home now a lot of engineering data from the flyby, as well as data from our plasma, our in situ instruments, our student dust counter, and header data to go with the images and spectra that we've already got. And so for the next couple of months, until we reach mid-September, it'll only be occasionally that we'll have new images on the ground and available to release. But starting in September, the spigot opens again. And then for about a year, maybe a little bit more, the sky will be raining presents with data from the Pluto system. It's going to be quite a ride. We're really happy about the amount of interest in this mission. As a mission team, we're excited to share it with all of you. And we're going to do some of that right now. We're going to get right into the science. For some of you, if you're seeing a cardiologist, you may want to leave the room. There are some pretty mind-blowing discoveries that we're going to talk about. And if I can have my second graphic, I want to show our 2x2 mosaic of the Pluto system. This has twice the resolution of the previous best global image of the approach hemisphere. And really, it's just mouth-watering. The level of detail is spectacular. This image has a resolution of about 2.2 kilometers per pixel. And I think just looking at it, you can tell, as our science team can, that Pluto has a very complicated story to tell. Pluto has a very interesting history, and there is a lot of work that we need to do to understand this very complicated place. I want to stress that. I want to drive it home by showing you this image at higher magnification. So if I can go to the next time step, we're going to look at just the northern half of that image. And we could easily blow it up even further. And you can see across the northern terrains here, which include the North Pole, by the way, and, this is a true color image, essentially true color as your eye might see it, a whole range of geologic expression. Kathy and Bill will be talking about this quite a bit more, so I won't steal their thunder, but just let your eyes gaze from the left on the western limb across the disk over to the east, and you can see different geological units, different kinds of features. It's telling that complicated story again, which is there for us to unravel. And if I can have the next time step and we can go to the south, you see a still more complicated story with the great equatorial dark regions, with Tombaugh Regio, as we informally call it, the heart on Pluto, and what look like massive tectonic features, both radially emanating from Tombaugh Regio, as well as others that run more or less north-south. You'll hear more about that later. I do want to tell you about one aspect of the interpretation that we've been making over the last week in looking more carefully at the imagery of Tombaugh Regio, or the heart. Like a real heart, it has two lobes on the left and on the right side. The left is the western side, and I think even to your eye you can distinguish a difference between those two. The right lobe looks like a much thinner deposit that's been painted on top of the topography. And our interpretation of that material in the right lobe, as well as the material emanating to the south below the western lobe, is that in both cases we believe the source for that material is the western lobe, that its material is being, bright material, probably nitrogen snow, is being transported off the source region of the western lobe, but perhaps by winds and aeolian transport, perhaps by sublimation and winds and then recondensation, or perhaps by a process we haven't thought about. But in any case, we think that we're coming to understand this feature just a little bit. It is early days. Bill may have a little bit more to say about that. What I want to talk about next is our next time step, which is a false color image, which has really been stretched to show the dramatic differences in color units on Pluto and how they correlate with the geology. This is pretty mind-blowing. Kathy's going to have a lot more to say about it and what it means in the bigger picture. But as you can see, for example, Tombaugh Regio with the western and eastern lobes that I was just talking about have different colors. They're telling us something in that. And soon we'll have composition spectroscopy to support that at very high resolution. You can see that the polar regions have a different color still, and that as we get down into the dark equatorial regions, there's still more information. The geology and the color, probably the composition, seem to be correlated. And this tells us that the payload that we brought to bear on the reconnaissance of the Pluto system was really the right payload, because we have on board the spacecraft now tremendous data sets with higher resolution color than this, higher resolution panchromatic mapping for doing the geology, and a spectacular data set with compositional information with over 64,000 pixels that we've put on the surface to get a spectrum at every location. We're going to be able to tell this story very well over the next year. Really looking forward to that. I'm going to move on to the next time step, tell you a little bit about atmospheric science, where we've also made some advances. This particular view graph is to illustrate something about our ultraviolet occultation of Pluto's large moon, Charon. This was an experiment that we designed years ago to look for an atmosphere around Pluto's largest moon. And there's been a pretty big body of literature speculating about how Charon could have an atmosphere. We just got the summary data down in the last few days. We don't yet have the full spectral data set. In fact, we won't have that data until September. But if you look at that time step, you'll be able to see the little yellow line represents the path of the sun as seen by from the spacecraft moving behind Charon. And you see it just clips the northern regions of the moon. That's exactly what we planned. That's exactly how we plan this trajectory to go. And just as you clip on either side of the body, you can see in that red and white graph that the light level from the sun just plummets straight to zero. Doesn't look anything like the solar occultation data that we showed you last week for Pluto, where we could clearly see a refractive signature, a slow decline in the light levels. Here, it's just basically a square wave telling us that Charon has much less atmosphere than Pluto, if any. We really can't put strict bounds on it yet because we don't have the spectra. But as I said, we'll be able to do that when we get out to September because those spectra will be downlinked. For now, all that we can say is it's a much more rarefied atmosphere, and that confirms our pre-flight notions, our pre-encounter notions, and we're really looking forward to seeing just how rarefied that is. It may be that there's a thin nitrogen layer in the atmosphere, or methane, or some other constituent, but it must be very tenuous compared to Pluto. Again, emphasizing just how different these two objects are, despite their close association in space. I want to also speak to another part of our atmospheric science, which is the fact that we've now got to the ground some of the radio occultation data for Pluto, where the Deep Space Network transmitted a powerful signal up to Pluto timed to arrive just as the spacecraft was passing behind the planet so that we could measure the refractive index of the atmosphere. And as you'll hear more from Mike, we got it. We got the data. They're beautiful data, and they have a wonderful scientific surprise. The pressure in Pluto's atmosphere, measured at the base of the atmosphere for the first time in history, is lower, substantially lower than predicted. And that's probably telling us a story, and Mike will have more to say about that. I'd like to close with one more time step. This is really a spectacular image. This is a silhouette of Pluto looking back after the flyby. I think this is just fantastic. This is our equivalent on New Horizons of the Apollo Earthrise photograph that proved we were there. You can only get this image by going to Pluto and crossing to the far side and looking back. Now, as striking and spectacular as this image is emotionally, it also represents a huge scientific discovery because you see above the dark disk of Pluto a band of light, which is actually telling us that Pluto has a haze layer in its atmosphere, and Mike's going to tell you more about it.
Okay, thank you, Alan. Good afternoon, everyone. I'm going to talk about two new results on the atmosphere that are basically changing the way we think about Pluto's atmosphere. We're having to start from scratch to understand what we thought we knew about the atmosphere, the way the weather worked and the way the climate and the evolution worked. So could I have the first time step, please? The first graphic, please. Okay, this is one of our first images of Pluto's atmosphere. Now, this was the image that stunned the encounter team. For 25 years, we've known that Pluto has an atmosphere, but it's been known by numbers. This is our first picture. This is the first time we've really seen it. This was the image that almost brought tears to the eyes of the atmospheric scientists on the team. Could I have the next step, please? Okay, now what I want to tell you now is what you're seeing here. This is the atmosphere backlit by the sun, and the light, the crescent that you're seeing, is light, sunlight scattered by small particles in the atmosphere. And these particles constitute a haze layer. Now the inset is a cross-section of that haze layer showing structure. The colors have been enhanced. They're not real colors, just so that you can see that there is structure. There is structure. There's an argument going on in the team whether this is dynamics or chemistry. It's probably both, but the real answer is that this is our first peek at weather in Pluto's atmosphere. Okay, could I have the next time step, just to illustrate that a little bit more? There's a hint that there is either a layer of haze at 30 miles, 50 miles, or a combination of layers and waves in this region. Those are the kind of things we're going to have to sort out over the coming weeks, and that's going to tell us about the details of how the atmosphere actually works. But the haze is extensive. It extends at least 100 miles above the surface. That is a big surprise. That's 5 times further than our models predicted. Models predicted that haze particles would form low in the atmosphere where the temperatures are cold, but it's forming high in the atmosphere where the temperatures are hot, or at least hot from Pluto's perspective. Which is not hot from our perspective. But nonetheless, it's a mystery. That's one of the things that we're going to have to sort out in the coming days. Okay, the haze is pretty. It's a way to see the atmosphere, but it's a piece of a big story that we're trying to understand from Pluto. And that is how the atmosphere and the surfaces are connected. So I have a simple animation to illustrate one aspect of that connection. Could I have the next time step, please? Okay, this shows how methane in the upper atmosphere is broken apart by ultraviolet radiation from the sun into chemical components, radicals and small atoms and molecules that react, trigger a set of chemical reactions that form complex hydrocarbons, like ethylene and acetylene, which were detected by New Horizons. As time goes on, these build up, they become supersaturated, and they should nucleate to form haze particles, which then grow, and eventually they will get big enough so that you'll see a haze layer and they will fall to the ground. At some point in this cycle, those haze particles are chemically processed to produce what we call tholins, which are chemically altered hydrocarbons that have a red color. And we think that that is how Pluto's surface got its reddish hue. And in a minute, Kathy's going to talk more about the color and the composition of the surface. But this is just one piece of that story. It's not a coherent piece yet. There are some mysteries. As I said, we don't understand why there's a haze layer at up to 100 miles altitude. It really is a mystery. Okay, the next story regards surface pressure, and I'll just give you a little bit of context here. In a planetary atmosphere, the surface pressure at any level is a measure of the weight of the air above that level. And weight is gravity acting on mass. So if you know the surface pressure of a planet's atmosphere, you can get a pretty good estimate of the total mass of that atmosphere. And it's important because that's a way of quantifying the global state of an atmosphere. Okay, so I can have a next plot, the next graphic, please. Okay, this shows surface pressure on Pluto as a function of time. Now the units might be a little bit strange to you. They're in microbars. A microbar is 1/1,000,000th sea level pressure on Earth. And the time scale there is from 1989 up to just before the present. Now, what is interesting here is that in 1989, Pluto was at its closest distance to the sun. And now Pluto is moving away from the sun in its very elliptical orbit. As it moves away, it should be cooling, the nitrogen should be condensing onto the surface, and the mass should be decreasing. But we don't see that. We see the exact opposite. That has been very interesting, nonetheless. We have been trying to figure this out. Well, what I'm going to show you now is a new data point, some more information that we have to add to this story. It is just one data point, but I do want to say it is significant, and we are going to have to figure it out. Okay, so this is it. This is what REX, the radio science experiment, has contributed to this story. A new data point which shows that the surface pressure is at most 10 microbars. That's an upper limit. So the mass, if you will, of Pluto's atmosphere has changed by a factor of 2. It's decreased by a factor of 2 in about 2 years. That's pretty astonishing, at least to an atmospheric scientist. And so that's telling you something is happening. Now, it is just one data point. These are early retrievals. We've got more data coming, as Alan says, and there's more to the story. But it's another mystery that we're going to have to deal with over the next few weeks, months, years, and so on. Okay, and now I'm going to turn it over to Kathy Olkin, who's going to talk about the color and composition of Pluto's surface.
Thanks, Mike. Yeah. So I'm going to tell you about the color and composition and try and tie this together so that you can understand what we know from this color. The color is really an indicator of different surface compositional units. So if I could have the first time step. This is that same false color image that Alan showed, and I'm going to talk through it and tell you what we're seeing scientifically and some of the things that we know and we understand from looking at this image. So first of all, you can see the dark region down at the bottom of the image. That's near the equator, and that's the darkest region. And if you remember, there's dark regions all around that area, even on the other side of Pluto. And then just above it, it's a little bit brighter and a little less red. And then at the North Pole, you see the brighter ices. So if I could have the next time step, putting this latitude and longitude grid on the image allows you to help see draw your eye to that banding pattern. Now I want to talk a little bit about it because it goes to the complexity that Mike was just talking about the atmosphere and the surface and the interaction. Pluto has a very complicated seasonal pattern of transport of ices. It takes 248 years for Pluto to go around the sun. And Pluto has a very eccentric orbit. So sometimes it's much closer to the sun than at other times. Also, additionally, Pluto's North Pole is tilted over at an angle of about 120 degrees relative to the plane that it orbits in. All of these factors together cause us different parts of Pluto to get different amounts of sunlight. And the sunlight is powering the sublimation of the ices from the surface into the atmosphere. And so some parts are kind of baked, like near the equator, and other parts receive these condensation of these ices, as you can see on the North Pole here. And so we've got a differing pattern that you can see manifested on Pluto that we understand from modeling of the seasonal transport of these ices. But there's one glaring difference in this pattern that I just called out, and that is Tombaugh Regio. Next time step, please. Tombaugh Regio clearly interrupts this pattern of latitudinal variation of colors and brightnesses. And one thing I should add is that those darker regions in the story I was telling of the seasonal transport are likely the tholins that Mike was describing that were raining out from the hazes, or falling from the atmosphere in the hazes. Now, what's really special about the Tombaugh Regio region is that we're seeing methane, nitrogen, and carbon monoxide ices there. This is telling us something that we need to understand. On the northern part of Pluto, we see methane and nitrogen, but not carbon monoxide. So maybe what we're seeing in Tombaugh Regio is a source region for some of these specific ices that complicates, in addition, the story of this seasonal transport that I was telling you about. We're going to be looking at that in the future. As you've heard, we have a small bit of our compositional data down, and we'll get a lot more information when we get the rest down. But we've got some great images, and Bill McKinnon is going to tell us about the geology of this Tombaugh Regio region in nearby vicinity.
Thanks, Kathy.
Sure.
Hi, everybody. Okay. Could I have my first graphic? Next, please. Well, we'll be looking at our fabulous near encounter hemisphere, and there you see it. You can start the animation. And what we have now is a full 7 frames of what will ultimately be a 12-frame mosaic at higher resolution, but not even our highest resolution that will come down later. This area, in the next slide, next. Yes. So this area, this mosaic covers in its entirety this vast, more or less flat, icy plain that we have been informally calling Sputnik Planum. It's pretty big. In fact, it's just about the size of the state of Texas. And all around the periphery and in the interior of Sputnik Planum are geological wonders, and I'd like to share some of those wonders with you. So could I have the next slide, please? So first, I'd like to look at that orange box or rectangle that you see at the upper left of the mosaic. Next slide, please. So this is the northern boundary of Sputnik Planum. There's a little scale bar down there, but basically this is about 250 miles across, about the distance between Kansas City, Missouri, and St. Louis, a city which I picked completely at random. Okay. Okay, next slide. So I've marked some things here to help sort of guide this tour. So most of the picture you see is really Sputnik Planum, and it's famous, or really well known, for having this sort of segmented or cellular structure. We just call it sort of polygonal or almost polygonal terrain. And you can see this really well as you move to the left side of the image where the contrast between the bright and dark shows up. But at the top of the picture, it's really different. There's a rugged landscape there, a degraded landscape, and something that to a geologist's eye looks like something that has been very deeply and extensively eroded. And we can tell it's old as well because you can see with your own eye various impact craters of large size. But what's really interesting to us is the actual interaction between the Sputnik Planum and this rugged terrain to the top. if you look carefully at the image, you can actually see a pattern that indicates the flow of viscous ice towards the scarp or cliff boundary of the rugged terrain. We call these streamlines, and when you look at these streamlines, which I've marked with those curved arrows that you see there, they look just like, and we interpret them to be just like glacial flow on the Earth. But I don't have to remind you that glaciers on the Earth are made of ice, like in Antarctica and Greenland. But water ice at Pluto's temperatures won't move anywhere. It's immobile and brittle. But on Pluto, the kind of ices we think make up the planet, which Kathy just talked about, nitrogen ice, carbon monoxide ice, methane ice, these ices are geologically soft and malleable even at Pluto conditions, and they will flow like in the same way that glaciers do on the Earth. So we have actual evidence for basically recent geological activity. Now, if I could just back up for one more thing, there's one arrow all by itself there. It's hiding up at the 12 o'clock position. We can actually see a flow of this, what is probably dominantly solid nitrogen ice, flowing through a breach in an old impact crater and partially filling in the interior of that crater. And like Kathy said, we knew that there was nitrogen ice on Pluto from spectra. We've known this for years. And we imagined that nitrogen was sublimating or evaporating one place and condensing in another place. But, to see evidence for recent geological activity is simply a dream come true. And I want to back up just one little bit and say, when I say recent, I don't necessarily mean yesterday. I mean geologically recent. But the appearance of this terrain, the utter lack of impact craters on the Sputnik planum, tells us that this is really a young unit. And we have models of what the flux of Kuiper Belt, small Kuiper Belt objects would be onto Pluto, and they give various answers. But the best ones imply that the ices of Sputnik planum and the flow features we see, in fact, I should even point out that those curved arrows up at the upper left there, we can actually see them going around what look to be barrier islands. It's really, to us, a kind of conclusive evidence for flow. But just to get back to the age is only a fraction of the total age of the solar system, probably no more than a few tens of millions of years. And what we know about nitrogen ice, what we know or can theoretically estimate about the heat flow coming from the interior of Pluto, there's no reason why this stuff cannot be going on today. Okay, so let's go to the next time step. So now we're going to go down to the bottom of Sputnik planum there and to that orange rectangle, and let's blow that up. This is a very busy scene, okay? And it's a bit bigger than the one I just showed you. So this one's about 400 miles across, so that's like taking a drive from LA to Phoenix, although it's not, it's a bit colder than that, I suppose. Anyway, next time step, please. So here's some things marked up. Actually, at the very top of the image, you can still see Sputnik planum. You can still see its polygons. And at the very bottom is this ancient, black, heavily cratered region, which we've been informally calling Cthulhu Regio. At the very right of the image, at the 3 o'clock position, are a group of mountain blocks, which we discovered last week, and we all informally named Norgay Montes. But in this picture, you can see kind of in the center, well, actually, if you go a little bit above in the center and then towards the left, another range or arrangement of mountain blocks. And these mountainous regions, two of them, are actually somewhat similar. You might think the ones on the left are different, but that's just because the sun is higher in the sky when that picture was taken, and so you don't see the shadows quite as prominently. The arrangement and appearance of these mountain blocks is similar from one region to the other. So we've given an informal name to this new mountain block after Sir Edmund Hillary, who with Tenzing Norgay first summited Everest back in 1953. The scientifically interesting and fascinating thing about this picture to me is that the Sputnik planum ice, these mobile ices, seem to have moved and surrounded and embayed the mountain, the Hillary Montes. And in fact, they cover up not just embay and surround the mountain blocks, but they extend all the way down, and they just seem to feather out just onto the edge of the Cthulhu Regio. And in fact, when you look at it in detail, there's a lot of fine structure in the ice between the Montes and the Cthulhu Regio, and a lot of fine structure that is different than the different scale, a finer scale than the polygons we see throughout most of Sputnik Planum. That tells us that the ice in that intervening region between the mountains and Cthulhu is substantially thinner. And in fact, one more fun thing you can see is that if you look just at the edge of the dark unit, you see sort of circles of this bright mobile ice. One's called infilled craters. So there are craters that have basically ponds of this probably dominantly nitrogen ice in them. Okay, so let's put this all together and let's take a flyover from one end of Sputnik Planum to the other. If I could have the animation, please. So we're going to start at the north, and we're going to careen over the cliffs onto Sputnik Planum. There are the ice flows around the islands down there. There are the polygons, well delineated. And as we move into the interior of Sputnik Planum, it seems like the polygons disappear, but they don't. If you look carefully, they're still there. They're just obscured by brighter ices. And in fact, we basically are approaching the region that is super rich in the carbon monoxide ice that Kathy was just talking about. Anyway, it's a long flight all the way to the south, so we'll skip over that part and we'll rejoin our tour here, coming up on the Hillary Montes. And there they are. We're sweeping across them, big blocks, small blocks, and bits. The Cthulhu Regio, the dark asphalt cone surface, ancient surface on the right. And as we move over the Hillary Montes, one of those big craters with the big ice pond is coming into view. That crater itself is about the size of the DC metro area. And as we move off the Hillary Montes, coming into view over the horizon on Pluto are the Norgay Montes. Now the screen has gone dark, but there's a whole lot more that we're going to learn about Pluto and its moons. Just as Alan said and Jim said, most of our images, most of our data are still on the spacecraft outbound from Pluto. And we'll be downlinking this in the months, in fact, over almost a full year or more ahead. With that, I'll give it back to you, Dwayne.
Thank you. Okay, so now we're going to transition into question and answers, and we're going to start here in Washington and then hit the phone lines and social media and come back. And Frank, I'm going to give you the first question because your expression is pretty cool stuff, right?
Thanks, Dwayne. It's Frank Mooring with Aviation Week for Dr. McKinnon. I have questions about a couple of things that I saw in the new disk image. It looks like a copyright mark just to the west of the plane. It's a big crater, I guess, with some concentric circles in it. If you have any idea what that might be, and then also just to continue on the ice flows, do you have elevation data as to what's making it flow, and is it flowing down into the mountains? Is the plane higher than the mountains?
There's a couple of great questions. So I think you're probably talking about, there are some circular features I didn't particularly point out in the full disk image, and to the west and to the north of Sputnik Planum and indeed of Tombaugh itself, and those are probably impact craters of some scale, maybe 150 or up to 250 kilometers wide. So some parts of Pluto are probably at least fundamentally ancient, even though there may be active geologic processes.
And isn't there a few with central peaks? Which,
well, those are smaller ones, but I think at the scale, looking at the big picture of Pluto, you'd be really looking at the very, very distinct circles. We'd have to look at.
I think he was thinking of the one we informally call Elliott Crater. You can actually even see it in this image there. So.
You mean the one just up at the 1030 position off the edge? Is that the one you mean, or? Mm-hmm. Or you?
Yeah.
Yeah.
Oh yes, that's another crater. Well, it's not really showing on my particular graphics, but it's another one of these craters that has bright ice in it, probably as a remnant, but it also has a central peak. So the central peak is dark and it's sticking up through a bright ring. And your other question was elevation. Yes, we measure the elevation of some of the mountains by just measuring their shadow lengths. And if we don't have shadow lengths, we use another technique called photoclinometry, which is basically determines the relative slope, and we integrate and determine, and it's called, and we get some estimate of the topography. And we can actually see on the Sputnik Planum that the individual polygonal cells are a little bit higher than the boundaries between the cells by a few tens of meters. But the primary technique we want to use is called stereo imaging, and we don't have our data yet to do that stereo analysis. But we are going to get more frames of that mosaic, and then we're going to get a whole sweep from an entirely different set of observations covering the whole, basically, of Pluto, and we're going to have a beautiful stereo view of whether, on the whole, whether Sputnik Planum is high or low with respect to things nearby. The one thing you can certainly tell, though, just by eye, is that the north, the Planum is lower than the cliffs, and it appears at the south where it's, let's say, it seems to onlap onto Cthulhu Regio, so it's kind of a gradational boundary.
Frank, did you have another question? You good? Okay. We'll go here, and then we're going to go to the phone lines.
Hi, yeah, Eric Ham with Science Magazine. If I could follow up with Bill, if I could get you to speculate maybe about what could be driving these flows and embayments, and also what how this source region got there to begin with. There's been debates, whether this is ices that have accumulated from above, layers of frost turning into, I guess, glacier-like things over time, or whether something is allowing ices to well up from within. So can you explain how this intriguing spot right in the belly of the planet got to be there, and then what's driving it? Thanks.
Well, you've sort of answered your own question, but we have a region, a vast region that seems to be truly a reservoir. I mean, it is. We describe this poetically as the beating heart of Pluto. I mean, it may be the supply zone, the supply hut for the entire atmosphere for a lot of geologic activity. Ultimately, how it was formed, you can imagine different things. You could go all the way back in time and imagine it was really an ancient impact basin, or maybe it's something else completely different. We see at the margins to the south, there's a jumble of mountains. There's highly deformed topography. We know that geological activity beyond just the flows that I've been talking to you about have deformed the crust there. We can't fully explain what's going on because we've only seen these 7 images close up. And so when all of the rest of that stuff comes down, and when we get some of this stuff uncompressed on the ground, we'll have a much more complete story. But you can imagine, as I use the word reservoir, you can imagine with any reservoir, I mean, it could be filled in from the side by glaciers flowing into it. It could be filled in from below. You could imagine that inside the icy crust of Pluto, there's enough pore space and cracks where nitrogen would actually be a liquid, because it would be warmer inside Pluto as it is inside all planets with respect to their surfaces. And this reservoir of liquid nitrogen could actually supply the planet. These are all interesting ideas, and as Michael was saying, it's very early days, and we're enjoying a great deal of animated discussion.
Yeah, and I'd just like to add one thing, which is that these images, nothing like these images existed just a couple of weeks ago, and we're sort of reacting to it in almost real time. But what we're learning, and very fundamentally, is that on Pluto, we have a much more intimate and intricate interaction between geology and the volatile transport and the seasonal climate cycles, those kinds of things that are forcing one another and feeding one another and creating a very complicated and layered story about the planet's history. And it's rare in the pantheon of objects in our solar system that we have seen this kind of an intricate and complicated story. I'm reminded in some ways of Titan, for example, but few other examples that are so dramatic. It's brand new.
Yeah, I mean, just you wait till the rest of those images come in, because I know there's going to be great stuff there.
Okay, let's go to the phone lines, and then we'll come back here for social media and any other questions in the audience before we wrap up. And on the phone line, first up is Ken Chang from the New York Times. Ken?
If you could remind me of the temperatures, what's the temperature in the Sputnik Planum that allows these glacial flows? What's the temperature of the atmosphere at the surface, and then higher up with the hazes?
You want to talk about temperature, Mike?
The temperature at the surface is about 38 degrees Kelvin, which is 380 degrees below 0 Fahrenheit. So that's incredibly cold. If you want to talk about the ices and the, ice temperature.
Yeah, well, but in case, even at 38 Kelvin though, solid nitrogen can creep, and below ground that nitrogen will warm up a little bit, and it's very sensitive to temperature. So there's nothing physically implausible about nitrogen glacial flow.
No, not at all. Even if there's just a modestly deep layer in Sputnik Planum, you get down just tens of meters, and it may be much deeper than that. The overburden, the pressure from the overburden of ice can actually change the properties of the nitrogen because it's getting warmer so that it's less viscous and much more able to flow. There may be even conditions where you can get liquid nitrogen flowing below a deep layer of ice of tens or hundreds of meters. And that may be part of this story as well, but we've got a lot of work to do to be able to say that with any confidence.
Okay, next up is Irene Plotz, Reuters. Irene?
Thanks, Dwayne. I have a couple questions. The first, I think, is for Michael Summers. I think I heard you say that the surface pressure measurements show that the Pluto atmosphere had decreased by a factor of 2 in 2 years. Could you just tell us what that 2-year-old data set is and how accurate that is compared to what you're getting with New Horizons?
Yes, the data that I showed, that time plot for Pluto's atmosphere, is based upon stellar occultations, where we follow the sunlight behind Pluto's atmosphere and look at the extinction of that sunlight to get a measure of how much gas is there. So we have to use those stellar occultations to extrapolate down to the surface to get a surface pressure. And that's what was done for each of those blue data points that you saw. As far as we can tell, those are accurate measurements of the atmosphere where the stellar occultation occurs. The thing that's different about REX is that with radio waves, you can go right down to the surface. And the data, the REX data, look extremely good. The error is really tiny, just a few %. So this should be our best measurement of the surface pressure on Pluto. Again, this is early. This is our first data. This is our first retrieval. We've got more studies to do on this. But taking it at face value, yes, it appears as if the atmosphere has changed in mass by quite a bit.
And Irene, just as context, all those blue data points, those stellar occultations, are data that was obtained from the Earth. Only the red data point is obtained from New Horizons. And so we're detecting what may be a really significant short-term variation in that atmosphere that might be a turnaround even. We'll have to see.
Now, what will really help, I think, is the most recent observations from SOFIA, which is, of course, one of our 747s that has a fabulous telescope that most recently, in the end of June, raced down to New Zealand and chased Pluto's shadow as it also was occulted by another star, and got a very beautiful occultation. And so that's a very recent occultation that could be easily compared with the Pluto data, for which it then might help interpretation of previous observations.
A really good point.
Irene, did you have a follow-up?
As far as the reddish hue and the theory that perhaps it's these chemically altered methane that are raining down these tholins, what would that look like if you were on the surface of Pluto? Would the particles be big enough to see, like snow or ice or frost? Or and also, why would they not be, or are they universally distributed, do you think? And then something else happens on the surface? And I know this is putting together a puzzle when you don't have the pieces, but just kind of curious what your thinking on that is right now.
Yeah, there's several questions there. One, in terms of what it would look like, we're talking about a very, very thin haze. If you were on the surface of Pluto looking up, you probably would not see it. We only see it when we're looking through long slant links through the atmosphere. And even then, looking at sunlight scattered off these particles is the way we're able to get that image. So it's a very thin haze, but it's distributed over a very large region. It appears to be like 100 miles or so high. In terms of the conversion of those particles to tholins, we don't know the exact details in that. tholins, that term encompasses a range of different chemical substances that appear to be altered hydrocarbons and nitrogen compounds that have been irradiated or that have gone through some chemical process where the hydrogens have been kicked off. So it's not a particular chemical substance. And so without having more detail, we can't really test the exact mechanism. But we do know that these substances are around. We see them on Titan, for instance. And the reddish color is fairly distinctive. So yeah, it's a puzzle. There are lots and lots of pieces, and the chemistry is certainly one of those pieces.
And I can add to address one part of that question that the person was asking, is that I believe there was also a question about the hazes falling, uniformly on the surface of Pluto. And that probably does happen. And so we have a lot of work to do to figure out the rate of that deposition. But the story of seasonal transport was the one that I think reveals why we see a distinct different pattern with these latitudinal bands. And it has to do with those tholins. They're darker. They're going to absorb more light. And so the ices will become volatilized. They'll go from a solid into a gaseous phase and then be deposited onto the poles, and so cover up perhaps the tholins that have been deposited on the northern pole. And so I think this is going to all be pieces of this puzzle that we put together to understand the rate of production of tholins and the deposition of it.
Irene, did you have another follow-up?
I do have kind of one other big picture question, which may be too early to answer, but for Alan, based on the data that you've gotten so far from New Horizons, can you say anything about the exact mass of Pluto and any changes in the models of what the interior may have? Thanks.
Thanks, Irene. I'm going to start that, and I'm going to ask Bill to chip in as well, because this is a particular area of his research interest. We have not been able to obtain a new mass estimate for Pluto, but before the flyby, ground-based data already gave us a very accurate mass. And in order to constrain the interior properties, the primary uncertainty was in knowing the radius so that we could get the volume and then convert to a density. And what New Horizons was able to really contribute, even as we were approaching the planet, was to discover what the true radius is. And it's 1185 or 1186 or maybe 1187 kilometers. So we had an uncertainty that ranged over maybe 70 kilometers. We've collapsed that to sort of plus and minus 2. And it's centered around 1186. So now that we know that it's somewhat bigger than many of us expected, that will lower the density and have implications for the interior properties, which Bill can speak to.
Basically everything Alan said is pretty much the case. We have decent masses for both Pluto and its companion Charon, and we have good sizes for both. And so we now have accurate density values. And so, in the past, years past, we thought that Charon was very icy and Pluto had much more rock in comparison. Now the bodies are, in fact, more similar. But Pluto right now still seems to be the rockier world of the two. And this will go into building new models and testing new models of the evolution of the system. In terms of what the inside of Pluto is, without gravity data, it's hard to be absolutely definitive. That's kind of one way we test our models of planets when we fly by them or orbit them. But everything we see, all the activity we see on Pluto, is consistent with the idea that it does have a massive rock core surrounded by a huge icy shell. And that icy shell then, by being a more icy planet, is probably a little bit thicker. And all other things being equal, it increases the probability that there may still be an ocean way down underneath a very thick layer of ice. Now that's a theoretical inference right now, but it's something that we're keeping in mind as we explore Pluto. One of the things we also learned, not just the size of Pluto, but we also learned that it was very, very close to spherical. We actually can't detect any oblateness or out of roundness in the body. And sometimes you run around the solar system and look at this satellite or that satellite, and they're very distorted. And this tells you about their history. Pluto probably was spinning very, very fast after what we believe to be a giant impact that led to the formation of its satellite. So after this formation, Pluto and Charon are very close together, much like the Earth and the Moon, and tides between the two cause the orbits to expand and the bodies slow down, and then they are now locked up the way they are. But Pluto doesn't show any evidence in its shape from this early fast rotation. So we think it must have been really warm enough that no residual shape could be supported. So it's still too early to say exactly, how hot, okay, and that kind of business. But that's the kind of thing that we'll be, applying our research tools, applying our theoretical models, and going to scientific conferences and writing scientific papers and either coming to conclusions or not. But that's how it goes in science. But things are looking good for Pluto, I think.
Hey, Kelly Beatty, Sky and Telescope. Kelly?
Thanks very much. I wanted to ask, because the atmospheric density is higher than you expected it to be, I'm wondering, I think this is for Michael probably, can you tell us anything about the possibility that argon is playing a role in the composition?
The REX measurements suggest that the pressure is about a factor of 2 less than previous measurements. So it's gone the other direction. We believe that the atmosphere has shrunk, to put it crudely. That by itself, I'm not sure says anything about argon. I don't believe at this point we have anything that we can say about argon.
Next, Jason Rehan, Spaceflight Insider. I hope I got the last name right, Jason.
That's all right, Dwayne, no problem. This one goes out to Alan. You called Pluto a couple times during this conversation a double planet. Considering that Pluto is larger and far more dynamic than previously thought, what does New Horizons findings say in terms of how we define what a planet actually is? This has been kind of a bone of contention with those who followed Pluto for some time now. So can you tell us a little bit about that? And thanks for doing this.
Yeah, sure, Jason. And not to sidetrack the conversation, but we call the Pluto system a double planet for a very specific technical reason, because the two objects are close enough together and their mass ratio is sufficient to draw the balance point between them out of the primary, out of Pluto, into free space between. That's exactly analogous to the way that we define a double star system, when the balance point, called the barycenter, is between the two bodies and not in the more massive of the two. The Earth-Moon system is sort of on the border. It's not quite there. In fact, the balance point, the Earth-Moon, is deep in the Earth's mantle, but not at the center of the Earth. So it's not yet moved out of the planet, but close. So I don't think there's any controversy at all about the double planet moniker. There's been this controversy where astronomers and planetary scientists have largely been on different sides of it. I think that you and the public, just like we on the science team, can pretty well tell what we're dealing with. It's very hard not to call an object like this, of this level of complexity, an atmosphere with potentially an internal ocean, certainly with complicated seasonal cycles, and certainly with a big complicated system of moons, a planet. And the way science works is individual scientists make their decisions one at a time, and eventually consensus is reached. And because we've made so many discoveries, both with missions like Kepler that Dr. Grunsfeld referred to, of different kinds of planets around the galaxy, and now a new class of planet in our own solar system, we're going through a period of transition. And those definitions are in transition as well. And it'll shake itself out, but one scientist at a time until we reach consensus.
Okay, Leo Enright from Irish TV, you're going to have the last phone question, and then social media is chomping at the bit, so we're going to get to the public around the world watching this program. But Leo?
Okay, Dwayne, thanks very much. Bill McKinnon mentioned a hypothetical ocean. I was trying to understand how that might fit into what you're seeing. To put it crudely, could you say that the nitrogen glaciers could be explained quite easily without a liquid ocean underneath, that other mechanisms could achieve this, but that Norgay and Hillary simply cannot be explained without something like that?
Okay, I should be very explicit. We don't have any direct evidence for an interior liquid water ocean from these images. What I was trying to imply is that our picture of Pluto as a complex active world, plus the fact that any massive ice mantle, if you will, on Pluto will probably be deeper than previous models, basically increases the theoretical likelihood that there might still be an ocean down there.
Okay, so let's see what the social media conversation and questions are. Emily?
Sure. This first question is from Derek, and he asks, what information is used to create these false color images?
Kathy?
Yeah, so the information comes from our Ralph instrument, and Ralph is two parts. It has a color camera and an infrared spectrometer. And the color images come from the color camera. We have 4 different color filters that's broadly a blue channel, a red channel, a near IR channel, and a methane channel. And they cover wavelengths from 0.4 to, say, 0.9 microns, where charge-coupled devices, CCDs, are typically sensitive. And so those images are a combination of those different filters combined, and sometimes we'll combine them to make it look like natural color, and other times we create a false color image so that you can pull out those wavelengths like the near infrared that's closer to 0.8 or 0.9 microns that our eye is not sensitive to, so that we can understand these compositional units in a detail that we couldn't with just our eye.
Great, thank you. This next question is from Linda, and she asks, the ring around Pluto is from its atmosphere. Would images of planets without atmospheres be able to be captured like this? And I think she's referring to the black image.
I'm sorry, could you repeat the question?
Sure.
What?
The ring around Pluto is from its atmosphere. Would images of planets without atmospheres be able to be captured like this?
Images without?
Like this.
I can take it.
You want to take that?
Yeah, I should say, yeah, sure, we've taken silhouetted images of other objects that don't have atmospheres, and then you don't see the ring extending above the surface. In fact, we have a very nice image that just came to the ground, hasn't been released yet. There are some optical artifacts because we're looking back into the glare of the sun that actually was taken about the same time, on the same day, closest approach day, that show the crescent of Pluto's big moon Charon. And there's no evidence of an atmosphere there whatsoever. You just see sort of like a brand new moon, just a thin crescent of light. It's quite a haunting image, and once we clean it up, we're going to make sure it's released.
Let's take 2 more, and then we'll close out here.
Great. This question is from Simon, and he said, is there a theory of what is driving the nitrogen ice flow, and could the sun's light be responsible even though it's so far away?
I guess that's for me.
There you go.
It's not sunlight, it's internal heat. If you have a thick enough, a massive enough layer of these kind of ices, whether it be nitrogen or carbon monoxide or methane, it will move. If there's a sufficient slope, it will move. In fact, we've done some theoretical calculations, which of course we need to do better ones, but we believe actually that one of our leading, I'll just put it this way, our leading model actually for the formation of the polygons at this moment is internal convective motion, rising and falling at a slow rate of the nitrogen ice within the Sputnik planum. As long as that ice is at least a half a mile deep, we think this process can operate. And I'll just say it's driven from the heat that is leaking out of the interior of Pluto.
Okay, I'm sorry. One more, and then give you the final one, Eric, then we'll close out. Okay.
Sure. This last question, when will we see the surface of the other side of Pluto in relatively high res?
Well, we've got about the best images on the ground already of the opposite approach hemisphere. The nature of New Horizons exploration of Pluto demanded that was a consequence that we were going to observe one hemisphere in exquisite detail and the other side in much less detail. And that's the combination of our very fast speed combined with Pluto's slow rotation rate of about 6.4 days. So the last time that we saw the far hemisphere, we were 3.2 days out, half that 6.4 days, and that corresponded to almost 3 million miles away, as opposed to the imagery that you're seeing that was taken when we were much more than 10 times closer. So the net is that we have a dichotomy in our maps. The far side is not imaged as well. We get the basic patterns. We can detect perhaps the largest craters on the surface and the largest units, but not nearly as well as on the close approach hemisphere. That said, we do have a good bit of imagery that's still on the spacecraft that'll help us improve the far side maps a little bit more. And in the fall, when those data start to come to the ground, we'll be able to produce a better map of that far side than we have now.
Eric?
Great, thanks. Yeah, Eric Ham with Science Magazine again. Atmospheric question for Alan or Mike. So this shrinking atmosphere, this plummeting pressure, does this? I'm assuming that if it got to zero, that means that the atmosphere froze out. Does this mean that you got there in the nick of time, and that that's where Pluto is heading towards a freeze out? And as a follow up to that, how can you reconcile a shrinking atmosphere with detecting haze much higher than was expected? That seems a little bit contradictory to me.
Talk about
a shrinking atmosphere with a much more dispersed or higher haze particles.
Okay, I'll talk about the haze first. The haze particles are extremely small, and they're very buoyant. They can stay up in an atmosphere. They can stay suspended in an atmosphere that's very, very thin. So you could have I'm just pulling numbers out of the air right here, but you could have the atmosphere pressure decreased by a factor of 10, and you could still have a haze present in the atmosphere. Now you could suspend less, but it could still be there. If you want to take the other part, I'll let you.
Sure. Well, for a long time, there have been atmospheric models and climate models for Pluto that suggested that as Pluto draws away from the sun, that the atmospheric pressure could precipitously drop. And in fact, during the time when the National Academy and other committees were looking at flying a Pluto mission and its relative priority, there was a real interest in trying to get to Pluto while it still had a substantial atmosphere. That helped motivate the case for why to get a mission launched in the 2000s versus waiting, because we wanted to get there while there was still an atmosphere to study. And eventually there came to be a sort of belief that, well, it's been 25 or more years since Pluto's closest approach to the sun, maybe there's not going to be any atmospheric collapse. What REx seems to have detected is or potential for the first stages of that collapse just as New Horizons arrived. It would be an amazing coincidence, but there are some on our team that would say, I told you so. So we'll see if this is in fact what's happening, or if it's a more complicated story, perhaps not related to atmospheric collapse or some other possibilities. As Mike said, it's early days. We have several more REx data sets to come to the ground that will help inform this question, because we actually got data from 2 different stations at ingress and 2 different stations at egress, and we only have one of those 4 and only part of that data set. So this is an unfolding story.
So that's going to do it here. As you heard today, Pluto is a very complex world. And as Dr. Stern mentioned, the data is raining down, and we will be bringing you more in the future. Stay tuned for updates on the cadence of how we will present that, share it with the media and the public and the world. And again, follow us on the NASA social media accounts, Twitter, Facebook, YouTube. Send in those questions. Keep them coming in. We'll get them answered with the science team at #AskNASA. And follow the conversation. This conversation is going to go on for a long time at #Pluto Flyby. And again, updates and any other type of information coming down in the future, www.nasa.gov/New Horizons. Congratulations to the team. Have a great weekend. And this team is not rewriting textbooks. They are writing the textbooks. Thanks for joining us.